You can start, sir.
In this lecture, we will start looking at forced convection past a mobile surface in the limit of high Peclet number. As I said the last time, we have already solved one such problem, and that is the correlation for diffusion into a falling film. Okay. If you recall, we had solved this problem. Okay, we had solved this problem by drawing an analogy between the concentration field in a falling film in which the surface is moving at a constant velocity v s, and that for the evolution of the concentration profile at a surface unsteady evolution when there is a step change in the concentration applied at the surface. Okay. And we had got this error function solution, and using that we had calculated the correlation for the Sherwood number in that case. You can do exactly the same thing here. Okay. You can do exactly the same thing here. Express C star is equal to C minus C infinity by C s minus C infinity, where C s is the concentration at the surface and C infinity is the concentration in the bulk far from the surface, with the assumption that the boundary layer thickness is much smaller than the width of the film. Okay. And therefore, I will get the surface velocity times partial C star by partial x is equal to the diffusion coefficient times partial z square C star by partial z square. And then I have to use differentiation by chain rule to express the variation of concentration with x and z in terms of the boundary layer thickness, the similarity variable z by delta x of x. Okay. Substitute that in there and use the same procedure as we had used for the flow past a rigid surface, except that the velocity in this case is non-zero at the surface. That I will leave as an exercise. What I will do here is the flow past a gas bubble, laminar flow in the limit of low Reynolds number. Okay. If I have a gas bubble of radius r, okay, in which there is a free stream velocity far from the bubble, okay, this is V f s, okay, this is the free stream velocity far from the bubble. And if the Peclet number is high, okay, I will choose my x coordinate as the direction opposite to the flow. R is the distance from the origin and theta is the azimuthal angle. This configuration has no dependence on the meridional angle as usual. Okay. In the limit of high Peclet number, where the Peclet number is equal to V f s times d by d for mass transfer, you would expect the disturbance due to the concentration at the surface to be restricted to a thin region close to the surface. And as we shall see in this case as well, there is going to be a wake, okay, in the downstream stagnation point. At the upstream stagnation point, we would expect the boundary layer thickness to be finite. Okay. Now, this is a forced convection problem. The velocity field is specified. Okay. In this particular case, you are given that in this configuration, the radial velocity V r is equal to minus V f s into 1 minus r by r. Okay. And V theta is equal to, I am sorry, there is a cos theta here which I missed. Okay. And V theta is equal to V f s into 1 minus r by 2 r into sin theta. Okay. These are the velocity components. Okay. Do the scaling as before. Okay, do the scaling as before. Okay. R star is equal to r by r. Vr star is equal to Vr by Vfs, okay, and V theta star is equal to V theta by this free stream velocity. And the boundary layer approximation in this case as well. Okay. The boundary layer approximation R star is equal to 1 plus delta, okay, star times eta. Okay. That is in this boundary layer, right, I have flow past the surface, okay, and the distance from the surface is equal to delta star times eta, okay, where eta is the similarity variable and delta star is the scaled boundary layer thickness. Okay. So, that substitution is made for R star. Okay. For R star you make that substitution, okay, and then this just becomes equal to 1 by R star, and the second term is 1 by 2 R star. Okay. So, these are the approximations for the velocity. And in here I substitute R star is equal to 1 plus delta times eta. Okay. I am sorry, I have plotted the velocity the opposite way, it should actually be downstream. Okay. Note that the velocity is going in this direction, okay, in the plus theta direction. Okay. The velocity is going in the plus theta direction, and this is delta star times eta. Okay. The scale distance from the surface is delta star times eta. So, these are the scaled velocities. So, if the scaled velocities are just obtained by dividing this by the free stream velocity. So, these are just the scaled velocities. Okay. Okay. And for R star I can substitute from here as I had done earlier. Okay. For R star I can substitute from here and I will get 1 by 1 plus delta eta. This follows the same procedure as we had earlier. First is we express the velocity in scaled form. In the expression for the velocity, we focus on a region very close to the surface of thickness delta star, okay, and approximate the R star as 1 plus delta times eta star, okay, very close to the surface. Use a binomial expansion to get an approximation for the velocity. Okay. Use a binomial expansion to get an approximation for the velocity. Okay. Here I will use 1 plus delta star eta whole power minus 1 is equal to 1 minus delta star eta. Okay. I just need to, in this particular case I just need to retain just the first term in the expansion. Okay. The second term is just equal to this term, the second term in the expression of V theta just tends to a half. Okay. With this I will get the approximations for Vr and V theta as Vr star is equal to minus delta star eta cos theta. Okay. That is the expression for Vr, okay, and V theta is equal to minus sin theta by 2. Okay. That is because I have 1 minus a half here. In the limit as delta eta goes to 0, I can neglect this term and I get 1 minus a half. Okay. So, I just get minus sin theta by 2. Okay. Note an important difference as I have shown in this figure on the left here, an important difference between the case of a mobile interface and a rigid interface. In a mobile interface, the tangential velocity is non-zero at the surface, as indicated by this non-zero value of v theta. There should be no negative sign, there is just a positive sign, like kindly correct that. The tangential velocity is non-zero, it is in the plus theta direction around the sphere, okay, as shown by the non-zero value of the velocity at the surface over here. Okay. In contrast, for a rigid surface, the velocity was 0 and the velocity increased linearly from the surface. The tangential velocity is finite. The velocity perpendicular to the surface decreases proportional to delta eta. Okay, it decreases and it goes to 0 at eta is equal to 0. The velocity perpendicular to the surface is necessarily 0 because of the no penetration condition at the surface. Therefore, the radial velocity has to decrease to 0 at the surface. The tangential velocity is, however, non-zero at the surface. Okay. So, these have to be substituted into the conservation equation. Conservation equation Vx partial c I'm sorry, I should use it for radial coordinate system, Vr star partial including only cross stream diffusion and neglecting streamwise diffusion. There is a balance between convection and cross stream diffusion in this case, okay. Because the boundary layer thickness is small, the flux perpendicular to the surface will be much larger than the diffusion flux along the surface. So, we have neglected the diffusion flux along the surface. Scaling this equation, okay, on the left side you can see that we will get V free stream, okay, by R into Vr star partial C by partial R plus V theta by 1 plus delta eta. Is equal to d by r square. 1 by r is 1 plus delta eta the whole square. Okay. Let me write this as delta x. Okay. Scaling the equations, r by r star and v by the free stream velocity. In this case, I have assumed that the concentration is Cs on the surface and C infinity far away, and I define C star is equal to C minus C infinity by Cs minus C infinity. Okay. The disturbance to the ambient concentration field due to the presence of this bubble at that location. Okay. So, that is the scaling that is used for the concentration. And multiplying throughout by r square by d, okay, the equation becomes Vfs r by d into Vr partial c by partial r plus V theta. and this term here can be written as half of the Peclet number, okay, where the Peclet number was defined as VFS into d by d, okay, where d is the diameter. Okay. We had VFS into r by alpha by the diffusivity on the left side here. So, I can write this in terms of the Peclet number as P by 2, where the Peclet number is defined on the basis of the diameter and not the radius. So, this is the equation. Now, I have to substitute r star is equal to 1 plus delta eta, okay, where delta star is the boundary layer thickness. Okay. Delta star is the boundary layer thickness. V r star is equal to minus cos theta delta star eta. Okay. We had just derived that over here, approximation for the velocity field, okay, and V theta star is equal to sin theta by 2, okay, where delta star is a function of the downstream coordinate. In this case, the downstream coordinate is theta. Okay. In this particular case, delta star is a function of the downstream coordinate, and in this particular case, the downstream coordinate is theta. Okay. So, I can substitute these here. Okay. Partial C by partial r star is equal to, okay, partial r star by partial I am sorry, dc by d eta, okay, is equal to one by delta star, okay, dc by d eta. Okay. The second derivative, partial square c by partial r star square, is equal to 1 by delta star square d square c by d eta square. And the derivative with respect to theta, okay, partial c by partial theta is equal to partial eta by partial theta dc by d eta. Okay. Chain rule for differentiation once again. Eta depends upon theta only through the dependence of delta on theta. So, this eta recall that eta is equal to r star minus 1 by delta star. Okay. Recall that that is a similarity variable. The distance from the surface, the scale distance from the surface divided by the boundary layer thickness, okay, that is the similarity parameter eta. Okay. So, this will turn out to be equal to minus of r star minus 1 by delta star square d delta by d theta dc by d eta. Okay. And r minus 1 by delta is equal to eta. So, I just get minus eta by delta . And all of these have to be substituted into the conservation equation. Okay. So, if I substitute all of these into the conservation equation, I will get P e by 2 into V r. Okay. V r recall was equal to minus delta eta cos theta. Okay. So, this is equal to minus delta star eta cos theta, okay, into partial c by partial r is 1 over delta, okay, dc by d eta, okay, plus v theta. Okay. V theta recall was equal to sin theta by 2. Okay. V theta recall was equal to sin theta by 2 over here, okay, into partial c by partial theta, which is minus eta by delta d delta partial c by partial eta. Okay. On the right side I have 1 by r square d by dr of r square dc by dr. Okay. So, 1 by r square 1 by one plus delta eta, okay, the whole square, okay, 1 by delta d by d eta, okay, 1 plus delta eta the whole square dc by d eta. Okay. And I have to have a 1 over delta here, because the derivative with respect to r is 1 over delta times the derivative with respect to eta. Okay. And in this I can cancel out delta eta in comparison to 1, because delta is small compared to 1 and eta is order 1. Okay. And over here I have to have a diffusion coefficient as well. Okay. So, no, there is no diffusion coefficient, because that is incorporated in the Peclet number here. Okay. That diffusion coefficient is incorporated in the Peclet number here. Okay. So, putting all of these together, the equation becomes Pe by 2, okay, into delta square cos theta, okay, so I should write as delta star square, it is a scaled distance, plus sin theta delta star by 2. Okay. Into minus eta dc star by d eta. No, this I should have a delta star here, because you can see on the first term these deltas will cancel out, okay, and on the second term I have 1 over delta times d delta by d theta. Okay. So, this is the expression for the concentration field, okay. And I can multiply throughout by delta square, okay, I can multiply throughout by delta square, okay, so that the coefficient on the right side is 1. If I multiply throughout by delta square, then I will get a delta square here, okay. Okay. And I will get a sin theta times delta over here. Okay. So, okay, delta star sin theta by 2. Okay. So, this is the equation for the concentration field. Okay. In order to get a similarity solution, this term has to be a constant in the limit as P goes to infinity. Okay, the limit as P goes to infinity, this term has to be a constant, in which case the equation becomes an equation, the concentration field depends only upon eta, with boundary condition C star is equal to 1 at the surface, eta is equal to 0, and C star is equal to 0 far from the surface for eta going to infinity, okay, subject to these two boundary conditions. Okay. So, I can solve this part of the equation. Okay. Okay. This constant has to, this first term here, the blue term here has to be a constant for a similarity solution. That constant can have any value. The solution in terms of eta will depend upon that constant, but the solution in terms of the original variables r and theta does not depend upon the value of constant chosen. Therefore, this constant can be chosen, selected to be 1 without loss of generality, okay. And in that case the equation for the concentration in terms of eta becomes minus eta dc by d eta is equal to d square c by d eta square. Okay. Okay. Substitute c star prime is equal to dc by d eta. Okay. I will get minus eta c star prime is equal to d c star prime by d eta, okay, which implies that minus eta d eta is equal to d c star prime by c star prime, okay, which implies that natural logarithm of c star prime is equal to minus eta square by 2 plus some constant a. Exponentiate this to get c star prime is equal to some constant 1 times e power minus eta prime square by 2. Okay. This is equal to dc star by d eta. Okay, this is equal to dc star by d eta. Implies that c star is equal to c1 integral 0 to eta. Okay. This should not be here, should be just eta square. D eta prime e power minus eta prime square by 2 plus some constant c2. Okay. The boundary conditions, c star is 1 at eta equals 0, c star is 0 as eta goes to infinity, that fixes these two constants. Okay. And the final expression is 1 minus integral 0 to eta. You can easily verify at eta is equal to 0, this is equal to 1 because the integral in the numerator on the second term on the right side is 0. As eta goes to infinity, the second term on the right side is 1 and therefore c star is equal to 0. So, it satisfies both boundary conditions. This term we had actually evaluated earlier. Okay. This is an error function. Okay. This is an error function which we had evaluated earlier, and the numerical value of this is root of pi by 2. So, you get 1 minus root of 2 by pi. Okay, so, this is the expression for the concentration field. Okay. What is the flux at the surface? Okay, the flux at the surface J r at r is equal to r is equal to minus d times partial c by partial r. Okay. Minus d into Cs minus C infinity by delta star times r, okay, times dc star by d eta at eta is equal to 0. Okay. And dc star by d eta at eta equal to 0 can be quite easily obtained from either this expression or this expression. Okay. The derivative of an integral is the value of the integrand at eta equal to 0. Okay. So, this is just equal to minus root of 2 by pi. Okay. Okay. Into minus root of 2 by pi. The slope is negative because the concentration is decreasing as you go away from the surface. Okay. So, this is the expression for the flux at the surface. Okay. We have still not yet evaluated what is delta star, okay, the boundary layer thickness, the scaled boundary layer thickness, which has to be obtained from this part, this blue part, okay, of the equation, okay, from this blue part of the equation. Okay. By setting this equal to 1, we have to determine what is the scaled boundary layer thickness. That we will continue in the next lecture. As you can see, the procedure is exactly the same as that for the flow past a rigid surface, except that the velocity, tangential velocity, is non-zero at the surface in this case. So, I will continue this, calculate the boundary layer thickness and then the correlation. That I will continue in the next lecture. I will see you then.